Welcome to Algebra 2, Chapter 6 review for the final. The learning target for these specific questions on the board is I can simplify radical expressions. So here's some notes to help you out as you do these problems. It says, remember, if the numbers are a perfect square or a cube, break it apart with 1. For exponent, see how many times the index can go into the exponent. That's the note that pulls out. The leftovers are stuck inside the radical. So when you come across a problem like this first one, you want to look at fractions to the fifth root. It's the same as raising everything to the 1/5 power. And so you want to find some way to get 32 to be some number to the 5th power. Well, if you know your multiples of 2, you know that 2 to the 5th is 32. So you can say, oh, that 32 becomes 2 to the 5th. A to the 15th, well, 5 can go into that 3 times, so it's really A to the 3rd to the 5th. And B to the 10th, 5 can go into that twice as well, so it's really B squared to the 5th. Now, if you're taking the 5th root of this, you can then use that index with the outside exponents to pull out those pieces. So a 5th root and a 5th power cancel and you're left with 2. The 5th root and the 5th power cancel and you're left with A cubed. The 5th root and the 5th power cancel and you're left with B squared. So we're left with 2A cubed, B squared. Now if we have even roots, that's when you have to pay attention to if our answer came positive or negative and think about even, odd. If you have an even, odd, that means you need to take the absolute value of it. So let's look at this first one. It says, if it has a square root symbol without anything else, it's a root 2, square root. And so 50 isn't a perfect square, but you can break 50 into 2 times 25. The reason being that you would want to do that is that 25 is a perfect square. Now, x squared is just going to, when you pull it out, that's going to be a nice one, but y to the 9th, you're going to pay attention to that one. You can break that up into y to the 8th and a y to the 1st. Now, if we look at taking the even root of the square root of all of that, well, we don't know the square root of 2, so that's going to stay in, but we do know the square root of 25, which is 5. We can pull out the square root of x squared, that's going to be x, and the square root of y to the 8th is going to be 4, because 2 can go into 8 4 times. Y to the 1st can't be pulled out, so it's left inside. Now, you have to think about if you have an even root, this was really a 2, so it's even, and you have an even power under the root. When you pull it out, if it becomes an odd power, you have to take the absolute value of it. The reason being that that number can't be negative, and you need to account for that. So we're looking at this x value specifically. We took the square root of a square, and it ended up being to the 1st power, which means you really need the absolute value of that x. If we look at the next one, these are cube roots. We like it when they're cube roots. That means that we're able to think about absolute values because it's an odd root to begin with. And so what you want to do, if they're both underneath the same root, you can actually multiply everything inside. 6 times 9 should end up giving you 54. A squared times a to the 4th gives you a to the 6th, and b times b to the 10th is b to the 11th. Now you have the cube root. You want to think about any cubes that can go into 54. I happen to know that 27 can go into it, so it's really the same as 2 times 27. We have a to the 6. 6 is a multiple of 3, so we're going to leave that one alone. But b to the 11. 11 is not a multiple of 3, so we can really split that up in b to the 9th, b squared. Now when we take the cube root of that, we can pull stuff out. The 2 once again gets left on the inside, but the 27 comes out as a 3. A to the 6 comes out as an a squared. B to the 9th comes out as a b cubed, and b squared gets stuck all alone in there as well. And we end up with 3a squared b cubed and the cube root of 2b squared. Now, radical expressions can also be expressions like these two here, where you're adding and subtracting, or you're multiplying a set of binomials. Remember, you can only add and subtract like radicals. Worst case scenario, if you really can't figure it out, type it all in your calculator and find the magic piece. So when we have problems like this, we want to pull out whatever we can. 32. Well, I know that 32 is the same as 16 times 2, and 16 is the square root. You can pull out that 4, you get 4 root 2. 50 is really 2 times 25. 25 is a perfect square. You can pull out that 5, you're left with that root 2, plus 7 root 2. Now, the purpose behind pulling out all that 4 and that 5 is that now all of these are times root 2, which means I can combine all of the numbers out in front. So I can go 4 minus 5 plus 7. 4 minus 5 is negative 1. Negative 1 plus 7 is 6. I have 6 root 2. You can tack on the root next one, if you set this up, what you want to do is you want to FOIL. So we're going to multiply the 2 by the 3 and the negative root 7. We get 2 times 3 is 6. 2 times negative root 7 is negative 2 root 7. 7 root 3, 7 times root 3 is just plus 3 root 7. We get root 7 times negative root 7. Now, a positive times a negative is a negative, but 2 roots that are being multiplied by 2. When we have square root 7 times the square root 7, those 2 roots, they're the same thing, you're multiplying them. Really, those roots cancel and you're just left with a 7 there. So we have 6 and a 7. So minus 7, don't forget to bring that negative down, but now you can combine those 2 in the middle. Negative 2 root 7 plus 3 root 7 just gives you root 7. Now, if you stop and look, this answer doesn't appear up there because you need to combine your 6 and your negative 7. Negative 1 put plus root 7, and that looks like this. Pretty straightforward. Just be careful with your negative, and remember that root 7 times root 7 is 7. Let's move on to the next one. So the next thing to talk about is when you have rational exponents, you can just type things into the calculator if necessary, but we don't really need to do that, guys. We can do this in our heads. Because if you have a fractional exponent form like this, it's really saying you're raising it to the 3rd power, but you're also taking the square root. And so you can kind of do that in any order. You can say it's 25 cubed root 2, or you can say it's 25 root 2 cubed. Now, personally, I happen to know the square root of 25. I really don't think you as well. I would start with this first way of doing it. The square root of 25 is just 5, so you get 5 cubed, which is 125. That's much faster than doing things like the calculator. Now, if we look at this next one, it says negative 64 raised to the negative 2/3 power. So, first thing you should do is take care of that negative exponent. Remember to take care of a negative exponent. It doesn't change the value, but it does bring its location. It doesn't change the positive and negative value. It changes the location of our value. So it's going to now go into the denominator. Now, 64 squared is kind of a hard one to do, so we're going to start with thinking about what 64 cubed is. 64 cubed, the cube root of 64, sorry. The cube root of 64 happens to be 4. So if you take rid of that cube root first, you end up with negative 4 squared, because we still haven't taken care of that square. So, negative 4 squared ends up giving us 16. We just have 1 over 16. You can check your work on your calculator when you're done. The only issue that we'll come across with that is you might end up with a negative 1/16 if you forget to put your negative 64 in parentheses. So be careful with that. Alright, the next other target is that you'll be able to solve radical equations and equations with rational exponents. So before we start canceling and moving stuff around, we have to isolate the root. So we look at this first one, it says square root of 3x plus 4 all plus 1 equals 8. We want to get that square root on its own, so in order to do that, we have to move that plus 1 over. We move that plus 1 over, we subtract 1 from both sides, and we end up with 7 on the right. Now we have the root isolated. And now we can get rid of it. To get rid of a square root, you square it. And you not only square the left side of the division, but also the right side. That gives you 3x plus 4 equals 7 squared is 49. Now we just start doing some pretty basic algebra to solve. 3x equals 45, meaning x equals 15. And the issue that comes across with a problem like this is that once you square something or raise it to a higher power, you can introduce what we call extraneous solutions. And so what you have to do is you have to double check that your answer works in the original problem. So back here, I'm going to plug in a 15. 3 times 15, square root of that, plus 1 doesn't equal 8. Oh, I got it, plus 4. There we go. 3 times 15 is 45. 45 plus 4, square root of that, plus 1. That gives us a square root of 49, plus 1, which equals 7, plus 1, which is 8. That's exactly what we wanted. Our answer works. Now, when you have a rational exponent like this next one, 5/4, much like to get rid of a square, to get rid of a square root, you square it. What we're going to do is we're actually going to multiply everything by the reciprocal exponent. So if we take everything to the 4/5 exponent, that's going to get rid of it, and we're left with x minus 5. Now, you can take it, do it part by part and just take the fourth power and then take the fifth if you want. You can do it whatever way you want, or do it all at once. I like to do it all at once. Now, 32 to the fourth power is going to be a large value, but 32 to the 1/5 power is the fifth root of 32. Fifth root of 32, we should know by now, is 2. So we get 2 now to the fourth power. Well, that's 2, 4, 8, 16. So x minus 5 is 16. X equals 21. Go back, make sure your solution makes sense. 21 minus 5 to the 5/4 power. That's 16 to the 5/4 power. Well, the fourth root of 16 we know from earlier is 2, because 2 to the fourth is 16. And so we get 2 to the fifth power, which we know is 32. Check, our solution worked. We didn't introduce any extraneous solutions in this case. That's everything on the page. Halfway done with this video, guys. Alright, here we go. Learning target and form function operations. We didn't like these ones, so be careful with this. Make sure as you're doing these that you're paying attention. We have two functions, and we perform the function operations. We're going to take the first function and subtract the second function. Now, you have to be careful in subtraction and division. Right after first function, 3x squared plus 4x minus 1. And when you subtract that g of x function, the whole thing needs to go into parentheses. So you're subtracting the whole thing. Otherwise, you may only take the opposite value of x squared rather than distributing it in the negative. And so right away, that's the first thing I started doing is I distribute that negative through. Now I have 3x squared plus 4x minus 1 minus x squared plus 3x minus 5. Combine your like terms, 3x squared negative x squared gives you 2x squared plus 7x minus 6. And that's all they want. You're not writing any zeros, you're not factoring, anything like that. You are done. So, use another question like that. It says x squared plus 6x plus 8 is your f of x, g of x is 3x plus 6. Find f divided by g. And its domain. That's a big piece. So, it's pretty basic. We start with x squared plus 6x plus 8 divided by our g, which is 3x plus 6. Now, as soon as you start dividing two functions or doing things like that, you start to introduce, you have to change their domains. So you have to think about the original two functions. Is there anything restricted in their domains? In a quadratic, there are no restrictions, and in a linear, there are no restrictions. And then you look at their new form. When they're together, is there anything that should be restricted? Well, if you're dividing, you have an x in the denominator, whatever's going to make that part of the denominator 0 should be a restriction. And so, when you look at that, if x was a negative 2, we'd have 3 times negative 2 plus 6, that gives you 0. So your domain, you're going to say, is all reals with x not being equal to negative 2. And there's the restrictions on your domain. Now that we've considered that, let's finish the problem. Sometimes stuff factors and cancels, and so you want to see if you can do that. So we're going to factor the top. We should get x plus 4, x plus 2 over, well, we can factor 3 at the bottom, x plus 2. Now you can notice, hey, the x plus 2's cancel. I'm left with x plus 4 over 3. You may ask, well, do I still have to keep that restriction if that there's no x in the denominator anymore? Yes, you do, because at one point in this equation, x couldn't be equal to negative 2. And so that restriction holds all the way through. So we're left with x plus 4 over 3, with the domain being all reals except x equals negative 2. Alright, we're doing a lot of these pretty fast. All comparative samples, so bear with me. This next one, at first glance, this might look like find fog of 3. But when they say f with this circle, g of 3, what they're really saying is f of g of 3. So it's f of g of 3. So what you want to do to start off with is take that 3 and plug it into the g function. So g of x, g of 3 is when x is 3 in that function. So everywhere you see an x, you plug in 3. The square root of 3 plus 1, that's the square root of 4, which equals 2. Now you take that 2, and what you now have is f of 2, because g of 3 is 2. And so you take f and you plug in a 2 into the f function. That's 2 plus 2 cubed. That gives us 4 cubed. these function compositions, you have to pay attention to make sure that all of the values are part of the domains of each of them. And so, if you look at this, we got g of 3 to be 2, and 2 is part of the domain of the function of f of x, so that's fine. It all worked out. 3/4 of the way there. So here's the next learning target. It says I can find the inverse of a relation. What an inverse is you take the x and the y values and you actually switch their places and you resolve the new equation for y. So inverses, you talk about those art with black and white being inverses. Sometimes they'll mess around with the black and the white and switch the shadows and switch the white. That's kind of what we're doing now. So when we have this function, we're going to take the x and the y and we're going to switch their places. So now x equals 3y plus 10. The directions say to resolve the new equation for y. That means solve the equation for y now. We subtract 10, subtract 10. X minus 10 equals 3y divided by 3. Now, you may see an answer look like x minus 10 over 3. But you may not. You may also see it written out as x over 3. Go back to that last problem, remember that it should be y equals plus and minus the square root of x minus 6 over 5. A lot of you probably forgot that plus and minus, so be careful with that. When you take the square root in a problem, you need to think about the positive and the negative root. And so, yes, that's not a function, but it is still part of the inverse equation. The inverse is not a function in this case, but it is an equation. So here it says learn target, I can graph radical functions. You can use a calculator to help you, but you can also just kind of think about this. Radical functions are weird. They have a point where they just start, right in the middle of your graph. And so that point is whatever's going to make it a 0 underneath that root. And so if you think about that, to make that a 0 under there, you need x to be negative 2. That's going to give you a 0. Square root of 0 is 0, which means you have a point at negative 2, negative 3 where you start. Right there. That is the beginning point. And then from there, we can find more values. Now, I typically pick values that are going to give me nice roots under there, so I might start with like a negative 1, because negative 1 plus 2 is 1, and the square root of 1 is 1, and then I get 1 minus 3 is negative 2. That gives me a nice point to graph. I might skip 0 and go all the way up to 2, because 2 plus 2 gives me 4. Square root of 4 is 2, minus 3 is negative 1. I've got another point in there, but I want to maybe get another value underneath there. Well, I know that 9 is the next perfect square, so 7 plus 2 gives me 9. Square root of 9 is 3. 3 minus 3 is 0. I get another point 7, 0. And from that, I have this nice curve. Now, you should only have an arrow going in one direction, not an arrow going in both directions. That is a bad approximation of that curve. Let me try that again. Looks like my board's off a little bit, but you end up with that. That is the end of the Chapter 6 final review notebook for Algebra 2. Make sure that you go and you review some of the stuff and practice with it on your own.